Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I'm delighted to have Jelani Nelson from MIT with us today. The work he'll describe on moment estimation in data streams is already quite well known. I've heard a lot indirectly about it, so I'm very happy we can hear it from the source. Please.
Thanks. Okay, so I'm Jelani. This is joint work with Daniel Kane and David Woodruff. And I'm going to start off just by defining the model for this problem. So we have an n-dimensional vector x. It starts off as the 0 vector, and you should think of n as being really, really large. Like maybe I'm indexing the vector by source-destination IP pairs or something. And I have a really long sequence of updates coming in a data stream. And each update is a pair. It's an index together with an amount. And it says add that amount to the corresponding index of the vector. And the amounts are all bounded precision integers. Okay? And the goal in this talk is to output the pth frequency moment of the vector x, where p is given up front. Okay? Okay, so, yeah, go, yeah. So imagine like, you know.
You're updating this vector, so n is not your time. Your time is...
N is not time. N is like, for example, okay, like here's an example. I have network traffic. Every packet has a destination and source IP, and x is indexed by these things. And then every time I see a packet, I like update the corresponding thing by 1. And now the vector tells me, you know, x sub I j is how many packets went from person I to j. Yeah, is the model okay? Yeah. Okay, so moment estimation gets used like in a black box way in a bunch of other problems. So one, for example, is empirical entropy estimation. So you imagine, again, this IP example. If it's indexed just by destination IP, you know, like the entropy tells me how skewed the distribution is, right? So if
maybe it's good for us to focus on what you feel is the most important example. So was it this IP?
Yeah. So from now on, think of being indexed by destination IPs, and think of v always being 1, and xi is just how many packets were sent to IP address. So then, let's say in like this application, you know, the empirical entropy of this vector now tells me something about how concentrated, you know, like the distribution is of where packets are going, right? And if it's too concentrated, for example, that could be a signal for a denial of service attack. So I mean, so this thing, actually, they use empirical entropy estimation to do these things, and the best known algorithm uses moment estimation as a black box, which is that's an algorithm I did with Nick Harvey and Krzysztof Onak. Okay. So I want to talk about, like, I guess, kind of how to solve the problem. So we give an optimal algorithm for this problem, and that's what I'm going to focus on. There are two natural objectives in developing an algorithm. One is I want to minimize the amount of memory I use in my algorithm as I'm processing the data stream. So if you think of n as being really large, the length of the vector as being really large, you don't want to have to remember the entire vector in memory. Okay. And also I want to minimize update time. I don't want to have to take too long to process every single packet or something. Okay, so there are two easy solutions that use a lot of space but have low update time. One is remember the whole stream, and then at the end of the stream calculate the answer, or there's also keep the whole vector in memory. Okay. Remember in little m was the stream length, and capital M is the update amount is bounded by capital M in magnitude. So this is just you know, like, how many bits do you need to represent a single frequency? Okay.
When you say keep the stream in memory and then calculate x afterwards,
Yeah.
Is there something clever you would do other than keeping X in memory at that point?
You mean this one? Or this one?
The second one.
Oh, I mean, if you don't care about the reporting time at the very end, you could keep the whole stream in memory and then just like loop over 1 to n and just like sum up the frequency and then just... You wouldn't use n memory, you would use little n. Is that what you're asking?
Well, I mean, I was just wondering like what we would do after you're done seeing the stream.
You could or you could like sort by the index, and then just like run through it once and accumulate.
I'm still missing something basically. Your goal is just to calculate the moments of the final vector x.
Yeah. Yeah.
So why would you want to keep more than x?
No, maybe n is much larger than n.
Yeah. You might also want, like, for some of these like network monitoring applications, you want to like ask what is the moment now, like periodically throughout the stream. So it's not necessarily always at the end of everything. But yeah, m could be much less than n, which is why this could be much better than that.
So for the example, the ideal example, what would p be?
P is something that's very near 1.
Okay.
Yeah. But not quite 1. And the reason is I can explain why this even like makes some kind of sense. The idea is just so there are these other entropies besides Shannon entropy, like there's Solis entropy, Renyi entropy, which are defined in terms of moments, and like just by L'Hopital's rule, they converge to Shannon entropy in the limit as p goes to 1. If I write down the definition of what they are, like define like h sub p to be like 1 minus f sub p over p minus 1. Okay, where this vector, this is f sub p of the normalized vector. Okay, so this is like the frequency, this is the probabilities. Then this thing, the limit as p goes to 1 of hp is equal to Shannon entropy. So this is the connection between moments and entropy. But if you just black box if you just use the fact that this converges to Shannon entropy, you're not going to get such a great algorithm. But there are some tricks you can use where you basically calculate lots of HPs and then interpolate and then evaluate some interpolated polynomial at 1. Okay. That's a really short summary of that. Okay, so I'm going to focus in this talk on minimizing space usage. Okay, and so there's one bit of bad news, which is that the first work that studied this problem by Alon, Matis, and Segedi, they showed that you cannot output the exact answer deterministically in sublinear space. So you need to allow for slack in 2 ways, and one is multiplicative error, and the other is you have to settle for a randomized algorithm that has some constant probability of failure. Okay. So this is our new goal, just out of necessity, if we want a sublinear space algorithm. And then even more bad news is that a polynomial space is required for large p. And so I'm going to focus, in this talk I'm going to focus on p between 0 and 2. And it's a real number, so this is not just 3 values. And p is not 0, so greater than 0. Okay, so let me tell you what was known before this work.
So that work also had a positive result, right?
Oh, Alon, Matis, and Segedi, yes. So they had a positive result. When p equals 2, they had an algorithm, which actually we show is optimal. When p is greater than, I think, 5, they also had some like... sorry. When p is greater than 2, they also had an algorithm, which has been improved upon since then. Yeah, they had positive results. Okay. So first, let me just recall this. This is our notation here. So previously, the lower bound. So this is all like number of bits of space you need to solve the problem. Okay, where you want a 1 plus minus epsilon approximation with say 99% probability. Okay, over the randomness used by the algorithm. So David Woodruff showed a 1 over epsilon squared lower bound And the original work of AMS showed a log n lower bound. And when p equals 2, this is one of the positive results that they had was, remember, frequencies can never be bigger than little m times capital M. So this is like the word size you need to store a frequency. So they showed that you just need 1 over epsilon squared words of memory. And when p is not equal to 2, Pyotr Indyk gave an algorithm which had log squared space. Okay, and there were some differences given by Lee later, but I mean it's the same bit complexity. Okay, so what do we show? We show that for all p between 0 and 2, this is the correct answer, both upper and lower bounds. And I should say that I'm being slightly pedantic. All bounds on the slide are hiding an additive log little n, which I'm not going to talk about. Okay. So are there any questions about statement of the problem and what we're going to try to show? I'm going to show you the upper bound. Oh, okay. So now I'm focusing on the upper bound in this bound. Okay, so the first thing I want to tell you about are p-stable distributions. So these are, this is a family of continuous probability distributions, and they're out there for all p between 0 and 2. Let's say they're indexed by p, okay? In reality, for each p, there's like a family of p-stable distributions, but let's say there's only one for each p, which is going to satisfy some property that I'm going to tell you about now. So I'm just going to define this distribution by a property it has, okay? And the property it has is that if you take any fixed vector x and take its dot product with a vector of independent p-stable random variables, so you take this sum over I, qi, xi, this itself is a random variable, which is p-stable, just with a scale factor, which is the LP norm of x, okay? So that's the only property I care that it has. And you've probably seen this for Gaussians, maybe. But they're out there for all p between 0 and 2. Okay.
I'm a little curious why you credit Zolotaro with this distribution.
Oh, yeah. So I've been told to fix this. Is it Levy who I should be crediting? Yeah, Levy. OK. Yeah, sorry. Yeah.
50 years earlier.
Yeah. I guess, yeah, I think I did that because he wrote a book.
Kinchin.
And then I forgot to change it to Levy. Wait, Levy and who else?
And Kinchin.
And Kinchin?
Yeah.
Oh, I see. Okay. Okay. Okay, so let me tell you about the algorithm. So it's going to maintain, you should think like dimensionality reduction. So rather than maintain the vector x in memory, I'm going to maintain a vector y, which is some linear map applied to x. Okay. And why can I maintain this in a stream? Well, if I can maintain the linear map A, basically whenever I see an update saying add v to the ith coordinate of x, I take v, I multiply it by the ith column, and I add it to y. Okay, so I can do that. Okay, and what is A? A is a vector of independent p-stable random variables. Okay, and the idea of using this p-stable sketch matrix for moment estimation in data streams was first used by an Indyk's algorithm. And he said, well, he's going to estimate LP, by the way, this is like p norm. I'm just saying take the moment, take it to the 1 over p power. Okay. He said estimate the p norm as the median of the entries. Lee gave a different estimator, which is unbiased and has lower variance and stuff. But and in both cases, the number of rows you need in this matrix is 1 over epsilon squared. Okay. Okay, so that's great. You just maintain this 1 over epsilon squared dimensional vector. The only issue is you need to store this matrix A, right? You need to consistently use the same matrix A over the stream. And naively, you need a lot of bits of space to store the matrix. And we're trying to get a small space algorithm. Okay, so what Indyk did in his algorithm was he didn't actually store A explicitly in memory. He stored some short random seed and used a pseudorandom generator to stretch the seed to get various entries of A. Okay? So at any given time, he was only storing the seed, not the matrix. Okay. And actually, remember his algorithm used something like 1 over epsilon squared times log squared space. And we're trying to get something like log space, 1 over epsilon squared times log. And the only reason his algorithm actually was so optimal is because of this step. The seed that he needed to store was the dominant space, was the dominant thing in his algorithm in terms of space. Okay, so you could just ask, well, is there a more efficient way to generate this matrix A? Okay, and what we show is that, in fact, yes, just via k-wise independence. Okay, so for fixed I, remember, so I have this matrix. For a fixed row, the entries in that row just need to be k-wise independent. And how do you generate k-wise independent random variables? You take a seed and you do stuff with it. Okay, and those seeds from row to row only need to be pairwise independent. Okay, so this is what we show. And we show that if you pick k to be something like 1 over epsilon to the p, then index algorithm, which took the median of the entries of the vector, works. And we also show that a different estimator works with a much smaller k, although algorithmically, I am still not aware of any reason why this is better. Like basically, this would give you the same, this would give you optimal space as well, and it would give you the same time as this one, if you do the appropriate tricks. But so yeah, so I'm just going to focus on this one. Okay. Good. Okay, so the remainder of the talk, I'm going to explain to you why this is true. Okay, so is it clear what I'm saying here, by the way?
Are you going to tell us how you produce these k-wise independent variables from the pairwise independent seeds?
Oh, I'm not really going to get into that, but I guess I'll say, so like let's say you want to generate k-wise independent random variables over some finite field, FP, okay? So you take a random degree k-1 polynomial, evaluate it at all the points, and that's your stuff. Okay. So what you're actually going to do is well, like Cauchy random variables, or not p-stable random variables are continuous, and I can't implement that on a computer. So the first step is I'm going to discretize the distribution to some precision, and then how do you generate a p-stable random variable? Like there are ways to do it where you pick a random angle and then you pick some random number between 0 and 1 and you do some trigonometric stuff. Okay? So you discretize, what you actually do is you discretize just like the unit interval 0 to 1. So you pick the discretized angle, you pick a discretized number between 0 and 1, and then now you can do the finite field version with this in this discretized way. Does that answer your question?
How are you building up pairwise independence to k-wise independence? Because with the polynomial, you seem more...
Oh, I see. Okay. So to get my k-wise independent random variables for a particular row, I need to pick coefficients which are like coefficient C0, ck-1, okay? And let's say this is row 1. And then I need to pick coefficients C0, 2 for row 2. Okay? And I'm saying, basically, look at this, just like concatenate the coefficients, and look at this as a single integer. Okay? And now I'm saying, like, these integers need to be chosen pairwise independently. So you can do that over a larger field. Basically, pick these seeds pairwise independently, and then now use the seeds to generate k-wise independent random variables.
The k-wise independence is within a row, but not between different...
Yeah, so if this is the matrix,
different rows?
If this is the matrix, then if you look at a particular row, these entries are k-wise independent.
I see, but you're not making an assumption about the k-wise independence along columns.
Oh, along columns? No.
There you only have the pairwise.
Yeah. Because, I mean, really, what is this matrix doing? It's, like here's my vector x, and here's y. Let's look at like a particular entry, this row. So if these were independent, then this entry would be a p-stable random variable. And I'm saying replace this full independence with k-wise independence. And now this is no longer p-stable, but I still want to say somehow it's good. Here. Okay, so the way I'm going to show you that this works is I'm going to analyze index algorithm under full independence in a way that exposes where full independence is being used, and then just replace it. I'll show you how to modify the argument. Okay. Okay, so here's an argument for why his algorithm works. Remember, it takes this ax equals y, and it looks at the median of the absolute values of entries of y. Okay, so why does that work? So let's assume the p-stable distribution, the median of the absolute value of the distribution is 1. Okay, and you can do that just by scaling the distribution. Okay, and now I'm going to define this indicator function of an interval, and let's look at one p-stable random variable q. Okay, so q is the sum over I of qi xi, and the median of, okay, so what is this random variable? Q is a p-stable random variable scaled by the LP norm of x. So this is the absolute value of a p-stable random variable, and the median of that distribution being 1 means this. That's exactly what it means, right? Okay. Don't anyone want me to draw anything? Or, okay. Okay, good. I'm not really saying anything except rewriting stuff. Okay, good. Okay, so how are we going to analyze the algorithm? Well, I'm going to take that interval -1 to 1, and I'm going to shrink it on both sides by epsilon. Okay, so I have this p-stable distribution. I said the amount of probability mass between -1 and 1 is a half. I shrunk it on epsilon by both sides. I'm going to lose theta epsilon mass. And similarly, if I stretch it by epsilon on both sides, I'm going to gain theta epsilon mass. Okay, and now what is this telling me? This is telling me that if I take enough trials, what's a trial? A trial is a row of this sketch matrix, right? If I imagine these are my QIs, and then this is sum over I of QI xi, and I'm doing a lot of different trials, okay? So what this is saying is if I take R trials, then the fraction, in expectation, the fraction of trials that are less than 1 minus epsilon times the LP norm is less than half of the trials. And the fraction of trials that are less than 1 plus epsilon times the LP norm, that's more than half the trials. So if everything were going according to what these expectations were telling me, like imagine that these weren't just expectations, but this is like what happened, then the median would be between 1 minus epsilon and 1 plus epsilon times the LP norm. Okay? So all I need to happen is that, like in fact, less than 1/2 are less than 1 minus epsilon times the LP norm, et cetera. So if I take enough trials, then that will happen just by concentration. Okay, and the kind of concentration you need is guaranteed by Chebyshev. Okay, so already I'm telling you that the trials, to analyze this, I only need Chebyshev's inequality, which means that the trials only need to be pairwise independent. Okay, so that's why the rows only need to be pairwise independent. Within a row, I'm using the fact that within a row I have full independence, because I'm saying this is a p-stable random variable, okay? And I know that if I take this p-stable random variable, I know how much mass is where. But if I only have k-wise independent QIs, then, for example, maybe a lot of mass is in this really tiny epsilon interval, and I shrink by epsilon, and something crazy happens. I don't know. Or I guess in this case, there's no mass there, and then I don't lose the epsilon mass. Okay. So the only thing I need to show to make sure that this algorithm works is I need to show that I need to show that these two expectations are approximately still the same to within epsilon in the case of k-wise independence. Okay? So this is, I guess these are called like invariance principles, right? So I'm showing some invariance principle. I mean, what is the expectation of an indicator function? It's like, I'm talking about CDFs here. So I'm saying the CDF is close if you have full independence versus k-wise independence. Okay? So that's what I'm showing. Okay. Good. So how might you show that? Well, you want to show that this expectation is similar under k-wise independence. Well, we know k-wise independence preserves expectations of degree k polynomials. Like that's what they're good for. Okay, so let me replace this indicator function of an interval with a well-approximating low-degree polynomial. Maybe sandwich it between two polynomials and use the fact that they're fooled or something like that. Okay. So we're not going to do that for a good reason, which I'm going to tell you soon. The good reason is that such polynomials don't exist, because these p-stable distributions, other than Gaussians, have infinite variance. So any polynomial is either going to be like a constant function or something, or it's going to have infinite expectation. Okay. So there are no such well-approximating low-degree polynomials under p-stable measure. So what we're going to do instead is we're going to well-approximate this indicator function of interval with some smooth function. Okay? And then I'm going to show you that the smooth function, or I'm going to show you some steps. I don't have time to show you the whole thing. That the smooth function is fooled by k-wise independence under p-stable measure. Okay? Okay. So I'm going to now talk to you about how to get this function. Okay. Okay, so switching context, I'm going to talk to you about FT-mollification, which I haven't defined yet, but I'm about to define it. Okay. I'm just curious, so have people seen mollification before? Mollification, yeah. Some. Okay. So okay, some have, some haven't. That's okay. So I'm not assuming that anyone has seen mollification. I'll tell you what it's all about. Okay, so the idea is this. I have a function f, which is not a smooth function. Okay, like for example, it's the indicator function of an interval, so it might not even be continuous. Okay, and I would like a smooth function which well approximates f. Okay, and there are these two facts out there. One is if you convolve a function f with a smooth function g, then all of a sudden the convolution becomes smooth as long as like these derivatives, as long as this integral exists. Okay. And this is some identity that the kth derivative is the same as f convolved with the kth derivative of g. And the next fact is that there's this, this limit of functions, the Dirac delta function. If you convolve f with the Dirac delta function, you get f back. Okay. So basically, the idea is convolve f with a smooth approximation of the Dirac delta function. That's mollification. Okay. And mollification looks something like this. You take a smooth function. This is my g, which is, there are smooth functions out there which are only supported in some finite interval. You take b sub c, which means shrink it inwards by a factor of c and make it taller by a factor of c. So as c goes to infinity, it looks like the Dirac delta function. You convolve it with f, and you get something smooth. Okay, that's mollification. Okay, so a problem with mollification. Problem meaning it's a problem for our particular application, is that, okay, the resulting function is a smooth function, but just how smooth is it? What are the derivative bounds that you get out of mollifying things? And you get something like, if you use a function which has some finite support like this, you're going to get derivative bounds which are like k to the k is your kth derivative. Okay? And c, remember, is this tuning factor where the larger I make c, this looks more and more like the Dirac delta function. Okay. So what we do instead is, so I said FT-mollification. We're going to take the same b, and rather than convolve with this, we're going to convolve with its Fourier transform. Okay. So this is b. Its Fourier transform looks like this. Looks like a sinc function, sort of. And we square it, and we convolve with that. Okay. And we're able to show, so you can show two things. One is that you get bounded derivatives. So I wrote k before, but so basically the lth derivative is like c to the l times 2 to the l, whereas before it was like c to the l times l to the l. And also you can write down some explicit bound on how close your indicator function is at any given point to the smooth function. Okay? And all this means is the larger you make c, the better of an approximation you get, which you expect, but you pay in your derivatives. And also, the farther away you are from the points of discontinuity a and b, the better approximation you get, which you also expect. Okay. And here's some plots. I'm making c bigger and bigger. So that's a small c, big c. Okay. Okay. So back to moment estimation. This thing only matters because, well, for this talk, because I'm going to use it to prove what I said about KY's independence. So how are you going to prove it? Okay. Okay, so suppose that R1 up to Rn are KY's independent p-stable random variables, and the QI's are fully independent. Okay? And look at sum over I, Ri, xi, and sum over I, Qi, xi. So this I know is a p-stable random variable scaled by the LP norm of x. And let's just say the LP norm of x is 1. Okay? What I want to show is that this is true. This expectation is within epsilon of that one. If I could show that for any AB, that would give me what I said in the beginning. Okay. And I'm going to show it to you via a chain of 3 inequalities. First, I'm going to move from the original function to the smooth version, then move to KY's independence, then move back to the original function. Okay? Okay. So why is the first one true? Okay, so this difference is at most the difference when I put the absolute values inside the expectation. And now I just think of some conditioning. So what is Q? You know, it's either within epsilon of the boundary points AB, or its distance from the boundary points is between 2 to the s minus 1 epsilon and 2 to the s epsilon for some s. Okay? So if it's within epsilon of the boundary, well, that happens with probability at most O of epsilon. Okay? And I know that these two functions are never off by more than 1 from each other. So that contributes at most O of epsilon to the error. And for the other case where the distance is between 2 to the s minus 1 epsilon and 2 to the s epsilon for some s, well, I just loop over all s's. I get this thing. And this is at most O of 2 to the s epsilon. And I get a geometric series, which becomes O of epsilon. Okay. Okay, so, and then the next inequality is some technical lemma which says bound independence full smooth functions. And the last inequality is very similar to the first. The only thing is you have to argue that under KY's independence, it's still the case that my KY's independent random variable will not be in a very small interval with large probability. Okay. Okay. So now I'm going to move to showing you this one, the second inequality. Any questions? So suppose I have a function f whose Lth derivative grows like alpha to the L for some base alpha. And I have KY's independence when K is large enough, both in terms of some error parameter as well as alpha. Then KY's independence fools f. That's what this says. Okay. Oh, question? Okay. Okay. Okay, proof strategy. So this is the thing that is not going to work, which is, well, I have a smooth function. KY's independence fools polynomials. I'll approximate the smooth function by a polynomial, and then that's fooled exactly by KY's independence, bound the error using Taylor's theorem. Okay, that's not going to work because, well, the moments that you get from Taylor's theorem are infinite, and also these polynomials, like, they have infinite expectations. So. Okay, so that's the problem that we had in the very beginning. So what are we going to do instead? Okay, so we just ask ourselves, like, why are the moments of this distribution infinite? And it's because it's a wide-tailed distribution. Okay, so we'll kill the tails of the distribution. Okay, so I'm going to define some new random variables, where as follows, and then I'm going to define some indicator random variable 1 sub s, which says, so 1 sub s is 1 when s is exactly the set of indices that got to be too big, and I truncated them. Okay? And now, from here to here, I'm just saying, at any point in my probability space, one of the 1 sub s's is 1, exactly one of them. Something got truncated. Maybe it's the empty set. Okay, and then I use linearity expectation. And then I say, well, if s is exactly the set of truncated indices, then the things not in s, Ri prime is still Ri. So this is equality. Okay? And now I want to say why this should look like some kind of progress. Okay? So the reason this looks something like progress is as follows. So wishful thinking, pretend that there's no 1 sub s here. Okay? Now there are two there are two problems we have. One is that we don't have full independence, we only have k-wise independence. And the other is, even if we had full independence, then our moments are infinite. So if we try to Taylor expand and bound errors, we'd get infinite stuff. Okay? So for I'm claiming that this should look like progress in terms of the second problem. So imagine we had all the independence in the world, and one sub s is not there. What I'd want to do is something like condition on all the ri's for I and s, okay, and Taylor expand about this point. Okay, and now my error term depends upon moments of this random variable. And this has finite moments because Ri prime has no tail. Okay. Okay, but I also have the problem that I don't have fully independent random variables. Okay. So I'm going to define new indicator random variables. 1 prime sub s says that s is a subset of the truncated Ri primes. And now in inclusion-exclusion, if s is the subset of truncated things, that means it's a subset and nothing else is a subset. Okay, so this is inclusion-exclusion. And then I'm just going to plug this in for 1 sub s on the last slide. Okay, so this is exactly what was on the last slide with that plug-in. And I claim like this looks like even more progress. Okay, and the reason it looks like even more progress is now, if I only have k-wise independence, suppose S union T is small. Suppose S union T has size at most k over 2. Okay? Then I can condition on all the Ri's for I and S union T. That determines this. It determines this. And I can Taylor expand about this and look at the k over 2th moments of this. I can Taylor expand to degree k over 2. Right? And I still have k over 2 independence left to look at moments of this. Okay. Okay, of course the problem is not all the S union T's are small. Okay. So the last thing that you do is you just ask yourself, well, how much error do I accumulate by just not including the sum over the large sets? Okay. So this is the approximate inclusion-exclusion, and what you show, unfortunately, this part just becomes like a series of technical calculations. So I'm not going to dwell on it, but basically what you can show is you don't lose much by doing this. Okay, so that's the idea. By the way, how long do I have? Another 20 minutes. Okay. Okay, and the very last step. So remember that was inequality 2, moving from full independence to k-wise independence. Okay. And now the very last inequality I said was similar to the first, but you need to prove anti-concentration. And maybe if someone really wants to know at the end of the talk, I can come back to it. But I'm just going to move on to some other stuff. Okay, so what did we talk about? So norm estimation, moment estimation, they're really the same thing up to raising things by p. So we showed that moment and norm estimation can be done in big O of this space. And I didn't really talk about the lower bound. And the main idea was just reducing the proof to showing this invariance principle for p-stable things. Okay? So any questions about what you showed? No? Great. Okay. So there are some other applications of FT-mollification, which I'm going to briefly sketch. One is pseudorandom generators for polynomial threshold functions. And so a polynomial threshold function is a function f, which I can write as the sign of some polynomial. And it was shown by Diaconi-Collis et al. That if you look at, let's say, x being from the hypercube, okay? If you look at x being random from the hypercube, uniformly at random, versus y having only k-wise independent entries, then as long as k is at least roughly 1 over epsilon squared, this sign function is fooled. Okay. And the proof outline was, well, my degree 1 polynomial p looks like some linear form minus a constant. Okay. And they have a reduction, which I won't talk about, which says we only need to consider the case where none of the AIs are too big. okay, in magnitude. And then they show the theorem for this regular case. Okay, and so with FT-mollification, you can show that in this regular case you need 1 over epsilon squared. You don't even need these logs. And it's basically the same proof I just showed you.
P of x is a polynomial, or is it?
Yeah, P of x is polynomial, and they looked specifically at the degree 1 case. Yeah. So they showed that for degree 1, when P is degree 1, you only need 1 over epsilon squared Y's independence, roughly. And you know, this would look like what I just showed you, because what is the sign? You know, what is the sign of something? It's what does the sign function look like, right? So this is the sign function. This is my f, and they're looking at f of sum of ai xi, right? This is exactly, and this really looks a lot like the indicator function minus 1, 1, and this is 0. This is the indicator function of minus theta. This thing is 1 when, you know, sum over ai xi is in theta infinity. So I just need to look at the indicator function of theta infinity. Right? Okay, and in fact, it's even a bit simpler than what I just showed you, because so let's define these random variables. I'm going to use the same chain of inequalities. The first inequality is the same exact thing, except now use the fact that you're in this regular case where no ai is too large, because you need to show that you know, like x is anti-concentrated. There's not too large probability that you're near the boundary. Okay, but anyway, this thing is basically exactly the same. The second step is just Taylor's theorem. You remember I said in the p-stable case we can't just Taylor expand because moments are infinite. But now we're working over the hypercube, so things are finite. You just use Taylor's theorem, and that's it. And the last step is the same as last time. So basically the same proof I just showed you. And in fact, you can also use FT-mollification to show that poly 1 over epsilon y's independence fools the degree 2 case. And recently, Daniel showed how to do it for any constant degree, but only under a Gaussian measure, not over the hypercube. Okay. I'll show you another thing you can do by FT-mollifying. So Jackson's theorem, some theorem in approximation theory. So what is approximation theory about? It's about approximating functions by simpler functions. And one example of a simpler function is a low-degree polynomial. Okay, so one natural question is, I have some function f, and I want to ask myself, in some set S, what is the best approximation of f by a degree k polynomial in L infinity or something? Okay. So here's a natural question. If I give you k, what's the best epsilon you can get? Okay, and Jackson's theorem says this. It says that if S is, say, the unit interval, and I define this modulus of continuity, which just says if 2 points are within delta, how much can f differ by on the evaluation at those points? Then this is the epsilon that Jackson shows you can get. Okay, and basically you can prove this just by FT-mollifying f and Taylor expanding to degree k, and that's the polynomial. So I'm not going to, you don't have to dwell on the details, but basically I just want to show you it looks like the same exact proof you just saw. Okay. So first I'm going to take this function g, which is basically f, and then I'm going to FT-mollify it. Okay. And now what is g of x minus its FT-mollification at x? I can just write it out. Ignore this m. Sorry. And now, okay, one thing that I should say is, like, what's one reason FT-mollification works? I'm convolving with the square of the Fourier transform of a function, and I'm going to normalize this square so that its integral is 1. Okay. So now that I have this function which is non-negative that I'm convolving with, and it integrates to 1, I can view it as a density function. Okay. And then I can say, well, actually, this integral is really an expectation under that density. Okay? And then now I can condition on this random variable y, where is it in that density? And then I can write something similar to what I wrote last time. And then I can use the second moment method. So that's really what FT-mollification is about, like why it works. And then you say, OK, well, G is close to its FT-mollification. Its FT-mollification is close to a polynomial by Taylor's theorem. You balance errors, which I'm not going to do in front of you. This is something you could go home and calculate. But basically, that's the idea, and you get the bound. Okay. And I'm just going to conclude. So I showed you space optimal moment estimation in data streams and some other applications of FT-mollification. In the algorithm that I just showed you, the update time, the time it would take to process every update in the stream, would be like 1 over epsilon squared. So one question is, can you get a space optimal algorithm which has constant update time? And it's known that is possible when p is 2. Okay? And for other p, in some newer work, we're able to get it down to at least being polylog as opposed to poly, but it's still not constant. Another thing is, so F2 estimation, that's the same thing as like L2 estimation. And L2, like basically maintaining a linear sketch and to estimate the L2 norm is very related to Johnson-Lindenstrauss. Okay, so can you get better things for Johnson-Lindenstrauss? That's another question. Another one is find more applications for FT-mollification. So I guess I'll just, if anyone has questions.
Additional questions?
Can you say a bit about agnostic learning?
Oh, OK, sure. So I do have, actually I have some slides up here. OK, so agnostic learning. So I have a domain and a distribution on the domain with like labels. And I have a concept class which I have functions mapping domain to labels. And OK, the optimal value for solving this learning problem is to come up with like the best function in my concept class, which minimizes like the probability of error. Okay, and I want to use as few examples as possible to get within epsilon of optimal. So what do I get? So I can get samples from this distribution, domain items together with their labels, and I want to get as few samples as possible to get to learn something good. Okay. And so there was some work where basically it says that if you can well approximate every function in your concept class by a low degree polynomial, then you can agnostically learn. Okay. And so actually their work was called, the paper was called Agnostic Learning of Half Spaces or something. And what's a half space? A half space is a degree 1 polynomial. And when I showed you this like k-wise independence fools degree 1 polynomials, basically what are you doing in there? You're FT-mollifying and Taylor expanding. That's giving you a polynomial which well approximates these half spaces. So that's the connection. So they show that if you want to well approximate an L1 norm, these half spaces, then to get error epsilon, you would need degree 1 over epsilon to the 4th. And what you can get from FT-mollification is degree 1 over epsilon squared. So that's the connection. That's the connection I know. Any other questions?
Can you say something about the anti-concentration?
Oh, yeah, sure. OK, so what do I want to show? I want to show that if I have a point, I want to show that the expectation of the indicator function of minus epsilon epsilon evaluated at R is still O of epsilon. Right? OK. So what I'm going to do is come up with a function which looks like this. So this is G. I want the property that G is greater than or equal to I sub minus epsilon epsilon everywhere. And I also want the property that the expectation of G of Q, this is the fully independent version, is O of epsilon. I want these two properties. Okay. I also want that I have good derivative bounds on G. Okay. Now, if I had these things, then what would I say? I would say, well, I know that this is true. I know that the expectation of G of R upper bounds the expectation of the indicator function of minus epsilon epsilon R, right? And I know that since the expectation of G of Q is O of epsilon and G has good derivative bounds, I can apply that smooth function lemma to say that the expectation of G of R is still O of epsilon. Okay? And that would give me that this is O of epsilon. So I just need to show you that such a function G exists. And such a function G does exist. And basically, you can take G to be 2 times the FT-mollification of minus 2 epsilon up to 2 epsilon. And you can sub C, where C is something like 1 over epsilon. Yeah.
So what kind of derivative bounds do you need here for G?
It's going to be something like O of 1 over epsilon to the L. So the L.
And could you use a Gaussian here for G, or that's not?
Yeah, so I think Gaussians would give you this L to the L derivative bounds. You mean like e to the minus x squared or something? Yeah, you'd get like L to the L kind of derivatives. So actually, I think there's like a theorem in complex analysis which says that if you want a function to have Lth derivative bounded by alpha to the L for all L, then its Fourier transform should only be supported in the interval minus alpha to alpha. So Gaussians would not satisfy. And this is why you FT-mollify. You basically, by convolving with the Fourier transform of a smooth function of compact support, you're killing the tail of
Any other questions? Thanks, Jelani.